Here we are again after the coffee break, and now we'll leave the floor to Dr. Anna Chiara Tizzoni, who is a physicist, and she has received this PhD in Material Science for Energy, Health and Environment at the University of Tor Vergata, and she has worked in ENEA since 2019 in the Solar Energy and Smart Network Division in Rome, and dealing with the study, the development, and the characterization of materials for energy production and storage. Please, Anna Chiara.
Thank you. Just a brief overview of the topic we are going to address in this lesson. As already seen by our colleague in this, at the beginning of this school, concerning CSP technology, molten salt can be used as heat transport fluid and heat storage materials in this type of applications. As you already know, molten salt mixture that are principal mixture of nitrites and nitrates are well known to have satisfactory thermal and physical features, and both heat exchange and storage in the temperature range concerned. And they are safe, not toxic, and available at low cost, and they are stable at relatively high temperatures. So the state of the art is concerned with the binary mixture that is named solar salt, and that is now currently most employed, and it is used as a reference material in this temperature range. Which is the main solar salt drawback? Its high melting point, because this high melting point can lead to very issues regarding operative works, because we need an heating system during the startup, and electrical heaters are expected to provide the minimum storage temperature tank. So it is very, very useful, and the research is going to investigate other mixture with low melting points that can be employed both as HTF or HSM. So the topic of this lesson is to define a proper selection criteria and summarize the state of the art about the main molten salt mixture, and to be applied for real life in the CSP application at medium temperatures. So we will focus this lesson on the selection criteria to evaluate feasible mixture. Then I will illustrate you briefly the main characterization techniques to detect the thermal, chemical, and physical properties. And I will show you just some results and comparison between the most commercial molten salt mixtures. So regarding the selection criteria, the key factor that we have to take into account are a good heat transport, a good storage efficiency, its cost efficiency, and also an environmental friendliness. Of course, the selection and the use of innovative mixture require a very good characterization regarding thermal, chemical, and physical properties. And among all these properties, the initial freezing temperature of the mixture is particularly relevant, because, of course, as already said, an high freezing temperature entails high operating risk for the entire plant. So the freezing temperature and the phase diagram of the molten salt mixture can be reduced by varying composition and including more components. It is very useful to make some consideration before starting, because of course we cannot choose all the mixture that we want because of chemistry. In fact, in general, molten salt that we can consider in this application consists of mixture of nitrites and nitrates, but only salts deriving from calcium, potassium, lithium, and can be taken into account, because other salts are very rare and very expensive. Carbonates or chlorides or other salts are very little soluble in molten nitrates, so their addition to the mixture is not very interesting. And the nitrates of calcium and nitrites of potassium, of sodium, sorry, cannot be coupled because there are some metaphysical reactions that can occur. And of course, we have to consider that mixture must be stable in air to avoid inert storage systems. So, all considered, we can start with the first selection step criteria, that is to define the working temperatures. The working temperature means to define, means to narrow the candidates by simulating the multi-component system with thermodynamic models. So, in fact, there are some models that can be used to predict the properties of different compounds without the need to perform long and expensive experimental campaigns. The results of these models are generally low melting composition zones from which it is possible to synthesize promising mixtures. So the mixture can be synthesized and can be characterized against their thermophysical properties. So regarding the lower working temperature, here I reported an example of the procedure using Wilson theory. In fact, using the approach of local composition models, it is possible to assume that the local composition around a molecule is different from the medium composition of the mixture. So starting from the coefficient of binary phase diagram that are very easy to find, to detect even in literature, it is possible to obtain a multi-component phase diagram. Here, for example, we obtain a ternary phase diagram. And to detect the low melting zone from which select the right composition and start synthesizing new mixtures. So the advantage of this approach is the possibility of predict the behavior of a multi-component system with only few experimental binary data. Then we have to define the upper working temperature, of course. In fact, as already said, by increasing the temperature, the molten nitrates undergo to a degradation mechanism, which in general can be divided in two steps. So firstly, nitrites and oxygen are produced, and this reaction is reversible, but nitrites can lead to a second reaction and producing oxide, and this process is not expected to be reversible. In fact, the oxide can accumulate and increase the melting point of the mixture, can react and produce very corrosive hydroxide and carbonates. It can precipitate, leading to problems, for example, with valves and pulp life occlusion. So the formation of the oxide is the factor that determines the upper temperature limit at which it is possible to use or not a molten salt mixture. So once we have detected a possible novel mixture, it is very important to characterize it against its main thermophysical properties. First of all, is very important to check the purity of the synthesized molten salt mixture. Within the Session2 project, I reported in this table the max percentage of impurity that can be allowed to use a molten salt mixture for solar applications. And then with the ion chromatography, it is possible to determine the major constituents of the mixture in aqueous samples. And thanks to microwave plasma atomic emission spectrography, it is possible to measure the presence of metals, even in small percentages. So once detected the purity of the mixture that we have synthesized, it is possible to determine the phase diagram by calorimeter techniques. In fact, applying a controlled temperature ramp, it is possible to allow the salt to melt and then solidify, and so detect the onset of solidification and melting points. The phase diagram can be also drawn thanks to some rheometer techniques. In fact, the dynamic viscosity of a neutron fluid and molten nitrate are these, is directly dependent on the material temperature. Another thermophysical property that is very important is the specific heat. Specific heat can be determined by calorimeter technique, considering a temperature range where the compound is stable and where no endothermic or exothermic process are present. We employed a protocol where the heat capacity can be evaluated by comparing with a standard of pure sapphire with an estimated experimental imprecision that is around 5%, depending on the temperature. The viscosity can be measured by a viscosimeter, and of course is a measure of the resistance of a fluid to deform under shear stress. As you already know, the viscosity is defined by this formula, and if the relationship between the shear stress and shear rate is a straight line that is passing through the axis origin, the fluid can be defined Newtonian, and the slope is the viscosity. Then it is possible to measure the density of the molten salt mixture. And in our laboratory, we employed an equipment that consists of a thermoregulated stainless steel container where the salt mixture is placed and heated. All the system is kept under air at atmospheric pressure. So density measurement of the mixture are performed with an Archimedean-based test. The temperature is regulated by an external controller, and the salt that is stirred and the cylinder is connected to a dynamometer, so the weight loss due to the buoyancy effect can be detected and noted. Regarding just a few words regarding the heat conductivity, in our laboratory we can measure the heat conductivity of molten salt only at room temperature, only for solid. We use a hot disk, and here I reported only the picture of some experimental tests that we are performing now. And the transit plane source is used both as heat source and temperature sensor. And the measure is made by recording the voltage change over the TSP element, while its temperature is lightly heated by an electrical pulse. So moving on the selection criteria step, once we have synthesized and characterized all the purity, all the main thermophysical properties of the molten salt mixture that we can consider, it is very important to take into account the third parameter that is related to the environmental safety and risk for human health. In fact, here I reported the risk phrases that are the indicator of the risk for the human and for aquatic life safety. And you know that a leakage of nitrites can produce problems in aquatic environments, given the fertilizer properties of the nitrate salts. And when we use sodium nitrite, it can lead to the oxidation of hemoglobin to a meta-hemoglobin. And here I compare it with a dithermic oil, because the mixtures that can contain sodium nitrite are more or less comparable regarding the risk to the dithermic oil. So we have to take into account when we insert this component to the mixture. The fourth parameter that we have to consider is related to the material cost. Here I reported some results that we inserted in a paper that we published, and it is based on self-made market research, but it is very useful just to make a comparison between the use of all components in the mixture. In fact, we can conclude that ternary mixtures with calcium, of course, is less expensive, but can be it can be a very good alternative, especially with respect to thermal oil, which is stable at the same temperature. The addition of lithium nitrate makes the cost of the mixture more or less comparable to the high-tech salt. And ternary with lithium that shows a very good thermophysical feature, including stability, but cannot be considered because it's very, very expensive. So we have to reduce the amount of lithium because it's not comparable to the other mixtures. So at this point, the most feasible mixture are further considered for costlier and time-spending tests, such as compatibility test with the CSP construction material, in particular corrosion test. Our colleague Elisabetta will explain later in detail the corrosion mechanism. Just few words, just to summarize all the scenario regarding the selection criteria of molten salt mixture. There are two main mechanisms by which material can corrode in the presence of molten salt: metal dissolution of the material constituents and oxidation of the metal to ions. So the oxidation is the main degradation mechanism that can cause uniform corrosion when a material is subject to a molten salt mixture. The corrosion behavior depends on the formation and the stability of the protective oxide layer over the material surface. In fact, you can see in these two same pictures that I reported that here on the left we have a problem because the surface layer that it's being created is going away, and it's not good because the salt can interpolate and can separate and create very, very high corrosion problem to the stainless steel. But you will see all this topic in details later. So just to summarize what we have seen, I would like only to give you an idea and to be critical regarding the choosing of material as novel mixture. The binary mixture containing sodium and potassium nitrites present, of course, low cost and good thermophysical properties. The ternaries containing lithium nitrates have some advantages because they have a low freezing point and thermal stability, but the main disadvantage, of course, is the high price of lithium nitrate. So the addition of calcium nitrate to this molten salt mixture can decrease the freezing point, but also the upper temperature limit. And the mixture, as we already said, the mixture containing the sodium nitrite are relatively costly and also toxic. And regarding quaternary or quinary mixture, the choice for now is limited only to the one containing calcium and lithium. But this because calcium nitrite and sodium nitrite cannot be mixed because there will be a formation and the rapid reoxidation of calcium nitrite even at low temperatures. So the mixture is not homogeneous. Here I reported some thermophysical properties of the main commercial and studied mixture that we published in a paper. And summarizing all the 5 steps that we have followed to choose a novel mixture, just to compare and to underline which is more important, we summarize all these results in a paper. I reported all the references here, and we can say that mixture with calcium nitrate are very promising both as HSM as HTF. Before concluding, I would like only to show some activities that are ongoing and that are part of a national project. we are developing and validating some predictive models, starting from the properties of individual components to establish and to determine the thermophysical characteristic of a mixture of nitrites and nitrates according to their composition. So we are performing, and we already finished an experimental campaign to fill the gap in the literature and to validate our models. So we built an open source database, and I would like to show you only the, I'm sorry that is in Italian now, because these results are going to be published in public domain, but I thought that for a school it could be useful, because I think that this database could be a very good tool, and we would like to that this tool will become open to all the users. In fact, we thought about 3 sections. The first one is the search section, in which we can search by chemical formula or compound all the main well-known thermal materials. It is possible, of course, to filter the research. In the second part of this database, it's possible to calculate, starting from the single components, the thermophysical properties of the mixture you would like to think. And in the third part, you can insert new data. Of course, this data should be validated, of course, but this will lead to a database that could be a very accessible and expandable tool. And we think that it could be very useful for our community, just to have a single and important tool for everybody. So thank you for your attention.
Thank you.
Do you have any question or curiosity, or wow?
Anna, I have a question, if I may ask.
Yes.
Regarding the last tool that you've been showing, which is very impressive, does new data that you add to the system enter the model in the calculation?
Yes.
Or is it, it does. So how do you avoid any bias from data that you have?
No, we are, the database is not online yet, and we are, you are saying that we have to check the, yes.
How do you control the data that enters? If we decide we want to add data.
We are thinking about it.
Okay.
Yes, of course. And we thought we can, we can maybe check the validity or the references, because all the data that are inserted are some references allocated. So we can check the validity of the data and approved. Yeah. And yes.
Yeah, great. Still a great approach. Thanks.
Okay. Thank you. So.
Thank you, Anna Chiara, for your very interesting presentation. And so let's now pass to the next presentation, and we will be given by Alexander Bonk. He is a chemical engineer specialized in material science. He has been working at DLR since 2016, and he is currently team leader at Material Research and Development on molten salt group. Okay.
All right. Good afternoon, everyone. Thanks for joining this interesting online or hybrid session. My name is Alexander Bonk. Thank you for the introduction from my current, from my last few years of R&D. I've been working in Thomas Bauer's group, who's also present here today, since 2016. We have a group that's quite neat in understanding molten salts on different levels of research. And so we are happy enough to have our own material science laboratories. That's 3 labs that we call our own in Stuttgart, where we do R&D based on a material level. And Thomas will introduce more research tomorrow, where we show R&D in the system level, featuring a large-scale facility of 110 tons of roundabout of molten salt. But I'm going to focus on the material science today. So just starting with a few nice pictures, what we do, we cover different aspects regarding molten salts. That's, for example, molten salt handling. We synthesize salt mixtures using, for example, glass box techniques. So this very fancy picture you see is the inlay of a glass box. We do salt purification. I'll demonstrate in a moment why. We do, in part, electrochemistry approaches. We use glass box routines, as you see. We then go further and we do long-term testing for molten salts. I also show you a bit of data later, which means we go into experimental design. We go into long-duration tests, for example, up to 5,000 hours of testing of salt mixtures under elevated conditions. We have been trying to automate many processes in the past. What is very keen for you today, what I will stress, is how important it is to be able to control temperature and gas phases in a molten salt experiment, and why this is important. And we do process optimization as well. Two main fields that we cover. You have a look at our infrastructure here. That's one of our oven laboratories. We cover two main things. One is molten chlorides, which are supposed to be the next generation molten salt for very high temperatures, where we talk about 700 degrees or more. And one is the state-of-the-art nitrates, and you've been seeing one temperature maximum right now, which is 565 degrees. Well, our goal in the past was to push this temperature limit to higher limits for multiple reasons. One is if you increase the delta T in your energy storage system, you have higher storage density in the same volume. The other is if you run a steam cycle at a higher temperature, your efficiency increases. So you would basically create two benefits at once. The downside is stabilizing the nitrates at higher temperatures is a real challenge, and I'll show you in a minute why. Following up on the nice slide from Jana this morning, and just as a backup as to what the application is, this is again the NOR plant. NOR in Moroccan stands for light, which makes perfect sense to me, what I learned only last week and never knew. So this is the NOR Ouarzazate plant, just to give you an impression again. Producing something in the range of 2.5 gigawatt hours per day of electricity, has a huge salt inventory. So whenever we deal with small scale things in the lab, up to maybe a few kilograms, here we talk about 140,000 tons of molten salt, which is quite tremendous, with huge storage capacities that we can ensure. I will not go into detail here. I had this slide since the morning before knowing what the others are going to present. You've been seeing the differences in direct and indirect storage, right? One important key feature here is that if you look into direct storage, you use molten salt as a heat transfer medium and storage medium. On the right side, in a parabolic trough field, for example, you use oil as a heat transfer fluid due to freezing risks, and you use the molten salt for storage because it's cheaper for the most part. The fluids, another repetition. If you look into the x-axis, you see the operating temperature range, and the bars basically tell you the range that these salts are operating in. I will only focus on solar salt today, just given the complexity alone. And you've had plenty of introduction. We talk about a salt with a melting point of 240 degrees. What is quite interesting, I can recommend this to everyone. If you ever have the opportunity to melt salts in a small glass beaker, do so, because they behave like water at room temperature. Very similar in its feature. There's only one issue, and you've been hearing the great presentation from Anna before. If you handle a molten salt for long periods of time in a hot environment, salts have a bit of a nasty feature, which is that they start creeping up walls. So if you have a hot surface, the salt will creep up the wall. It will leave crucibles. It will leave hot stainless steel tubes. Whenever the surfaces are hot enough, the salt will cover everything. And the other is you may have evaporation effects. That's something that's making experimental design extremely challenging, which is why when people enter laboratory scale experiments for the first time, they typically destroy their furnaces. That's the first instance they do. So they put a crucible into a furnace, and after 1,000 hours, they take out the crucible. The salt is gone, completely gone, because it's either evaporated or it's creeping into all the insulation, into the electric heaters, and then your furnace is destroyed. You repeat the experiment and try to understand what happened. That's one side. That's the experimental approach. The other is, if you look into these molten salts and you see a very simplified scheme here, the salt chemistry is what's determining long-term effects in an energy storage system that's often overlooked. If you look what's happening in the tank, you typically have a very complex chemistry what you see here, and I hope that I can actually, here. So this should be my, oh no, it's not correct. Well, can I get the laser pointer somewhere? I should be able to, right?
What do you need?
The laser pointer?
I think this.
Is it this one?
Pointer.
Ah, perfect. My Italian is not good enough to understand what the laser pointer is. Okay. If you look into this salt mixture, you start off with a nitrate salt. Nitrate meaning this is the NO3 anion, and you see that this is part of the anions that you can find in the salt. And other than that, it composes of the two cations, so the positively charged sodium and potassium. Now, in a two-tank system, you have a gas phase, right? The tanks are not filled to the top. They have a sort of gas phase. And during the day, you charge and discharge your hot and cold tank. You're going to push air out of the system, and you're going to take up air into the system, which is very important because what happens if you have the formation of some of these decomposition gases, on the daily basis, you're going to push them out, and you're going to breathe in fresh air from the outside, which means your tanks typically operate under a relatively pure oxygen partial pressure of, let's say, 20% in air, right? Now, why is that an issue? Now you heat up your molten salt, there's two things that are going to happen. The first is your nitrate salt is partly going to decompose into the so-called nitrite anion, which you've heard as well before. This is going to be accompanied by the release of oxygen. On a let's say thermodynamic basis, this is an equilibrium. To give you an impression, at 565 degrees, the amount of nitrites that you form is in the range of 5%. The oxygen that you produce leave the system. If you have a large-scale system like the one you've seen before, we talk about oxygen quantities of 100,000 plus cubic meters, pure oxygen leaving the system, which are entering into the environment. It's a pretty good oxygen producer. So what do the nitrites do? They principally have no harm to the system. They decrease the melting point ever so slightly, but they affect the high temperature limit also very slightly. Now, why is that an issue? It's an issue because the nitrites themselves, they form corrosive oxide ions, and there's a multitude of these. What you can understand is if these oxide ions are formed, typically this is accompanied by the release of nitrous gases, NOx gases. For the CSP plant, it's not an issue. Typically, you have post-treatment of every gas that's leaving the system just to reduce any emissions. Otherwise, it would be a diesel engine, which is why NOx gases are typically purified before they exit the plant. It's not an issue on a technical scale, but since you're removing the NOx gases, that means you're pushing this reaction constantly to the oxide side. It may not be an issue for 565 degrees because the rates are low, but if you go to higher temperatures, like we said, it will become an issue. The complexity here is that nobody actually understands the basics of this reaction. And the reason being is if you look into this diagram, you find different types of oxide species, which are labeled here. So the classical oxides, O2-, you find peroxides, which you all know from hair bleaching agents. Hydrogen peroxide is a very classical hair bleaching agent. The chemistry is the same in these molten salts where they are dissolved in. And then you have another impurity or another oxide species, which are called the superoxides. All of these are linked to one another by redox reactions involving the nitrates and the nitrites, which is making the chemistry extremely complex. Nonetheless, what is known is if the level of these increase, the corrosivity of the salt also increases. I'll show you later how this is going to work. There's going to be a talk later in terms of corrosion. What I want to stress here is that the chemistry you've seen before is detrimental for the corrosion process of every stainless steel that you find in the system. Yeah, typically the amount of nitrites and the amount of oxide ions that you find in the system, they determine how corrosive a molten salt is towards the metal. On the other hand, that means if you can reduce the impurity level of nitrites and oxides, you can also reduce the corrosivity of the molten salt and therefore reduce corrosion rates of stainless steels. And I'll show you later how this is working. So what do we actually do in the lab? What is part of our research? Something we've been doing is we've been trying to understand the thermodynamics of these nitrate salts. Thermodynamics meaning looking back into this nitrate-nitrite reaction, we've been trying to understand how many nitrites do form if we increase temperature and if we play around with the oxygen partial pressure. And this is what you see in this diagram. It's only a few data points, but each data point is something like 1.5 or 1,000 hours of experiments, single experiment with a fresh molten salt. So that's quite a lot of data that you see on the screen. And there's one trend that you see if you look at the nitrite to nitrate ratio versus temperature. What you see is the more you increase temperature, the more you go up in your nitrite levels. But the more you increase your oxygen partial pressure, for example, from 0.1, so that's 10% oxygen, to something like 80% oxygen, the more you can decrease your level of nitrites. And by decreasing the level of nitrites, the potential for forming corrosive oxide ions is also being reduced. You can express that in different forms of diagrams. This is a Van 't Hoff plot. I'll not go into detail, but it's one of the plots where you assess the thermal stability over an inverse temperature range. I'll not go into detail because it's not really relevant. Now, talking about the oxide ions, I told you earlier, you form NOx gases if you form oxide ions. Now, on the other hand, if you introduce NOx gases to your molten salt, you suppress the formation of oxide ions. And this is one of the diagrams showing that. You see on the y-axis the level of oxide ions, which is typically very low. We talk about sub% quantities over time. And you see different experiments at elevated temperatures. So you see these indications here. The first one shows temperature 600 or 620 degrees, which is quite elevated. And the second one is the NOx partial pressure that we applied in the purge gas stream for the molten salt. And what I want to point your focus to is that you see the red curve is a classical molten salt. You have no stabilization. You just purge it with air. What you see is that your oxide ion concentration, so the amount of corrosive impurities, increases almost linearly over time. That would be deadly for every system because corrosion increases. On the other hand, if you apply a certain partial pressure of nitrous gases, in this case, it's only 500 ppm in the purge gas, you see that your level of oxide ions in green stabilizes at very, very low concentrations, which is very substantial for the system, and which means that nitrous gases principally suppress oxide ion formation and potentially reduce corrosivity. Now let's look into corrosion. What you see here is not from a molten salt plant. It's just a nice image showing some sort of corrosion to highlight what can happen. If we talk about corrosion, we talk about two things. One is we understand degradation phenomena. One is we understand mass transport from molten salt to the surface of the steel and vice versa. And we want to understand redox activity. It's quite a complex process. How does that manifest in our research? Well, to give you an example, we've been performing high temperature experiments since, I would say, 7 years now. And one of the lessons learned is we didn't always use high temperature alloys or very sophisticated steels. For example, we had an experiment with a stirrer made of metal, and after 1,000 hours at 600 degrees, our metal stirrer looked like this. Yeah, very active corrosion, not intended. The stirrer was just gone. You can literally dissolve metals if you're not careful and playing around with these molten salts. That's nothing that we want to do. What we did after that is we replaced every metal component with a ceramic. To give you an impression how corrosion looks at elevated temperatures, I'm bringing a very short study to give you just a few hinges. We will compare how corrosion looks under almost state-of-the-art conditions, so operating at 570 degrees in air, that's state-of-the-art. What will happen if we increase the temperature in the same purge gas and not stabilizing the salt, leading to high degradation? And what will happen if we apply a purge gas that stabilizes the salt in terms of high oxygen and high NOx partial pressures? What difference that makes? To give you a first impression, you see the images of 3 test specimens. In this case, these are 2 classical austenitic steels used as, for example, hot deck materials, and 1 Inconel, very high resisting steel. Test condition 1, state of the art. You see the surfaces, they look quite oxidized, but nothing very detrimental. Going to test number 2, 620 degrees. You can see from the surface, that's nothing that you want to see. Yeah, you see pickles, you see some features pop up that indicate it looks like you left your bicycle in the rain for 2 years. Yeah, everyone knows how that is going to look. This is what this looks like. Even for the high range alloys, this is the same what you find here. Test condition 3, the same temperature as in red, applying a different gas phase. You see that the surface suddenly looks very clean again. You have some spelling here at the edges, but in principle, this is very comparable to test number 1, just by a change of gas composition at a very high temperature. Now, how does that play if we look a bit closer? What you see here is the same samples after removing the oxidation layer. So we removed the oxidation layer to look at the blank samples, and you see the same trends. You have a very clean surface here. You see these bumps and dents and so on in test number 2, and you have a very clean surface in test number 3. Looking at the oxidation scales under an electron microscope is what you see here. So when you go into an electron microscope, looking at the surface, what you will see is small particles. These are typically these iron oxides that you form at the surface, which are forming over time. What you see here, and what is important to highlight, these surfaces look very homogeneous, right? At least they look homogeneous to me. What you see in test number 2, your surfaces change very dramatically. This is the same what would happen, for example, if you would expose a steel to a very high temperature molten salt, even for small amounts of time. This is what can happen to the steel. It will form, for example, oxidation layers that then spell off, which is what Anna indicated. And spallation means as soon as your protective oxide layer falls off, the steel is freshly exposed to the molten salt, and it will start forming new oxidation layers from the already exposed fresh surface. And what you then form is these type of craters. Yeah, you form a crater that's starting to oxidize, and then you form pickles and so on. So if you see these surfaces under a microscope, that's never a good sign in terms of corrosion protection. Now going back to the oxidation layer under test number 3, just a change in gas phase. This is what happens at 620 degrees. You see that your surfaces, they all go back to a very homogeneous oxidation layer just by increasing partial pressures of oxygen and nitrous gases, which are very beneficial for corrosion. With that, I'll come to an end. What I want to show you today, and if you have any questions, I'm more than happy to answer them later. If you ever think about starting your own R&D on molten salts, I highly recommend to do so because there's not many labs doing these R&D activities for a few reasons. You need to think about experimental design extremely carefully, just because of the reason salts are creeping and evaporating. Keep that in mind. That's key to successful R&D research. The gas phase plays a tremendous role for molten salts. I hope that I could demonstrate today that if you apply the wrong gas phase, your salt might go to either very, very stable and non-corrosive or to very corrosive. You have two extremes that you can cover by only shifting the gas phase. I could demonstrate that salt degradation leads to corrosion. You've seen that at these high temperatures. You've seen it by the SEM images I've shown you before. But also that there is a chance for us, because whenever people talk about corrosion, there's also a chance for us to mitigate corrosion by thinking about intelligent gas management techniques. And this is the key to the next generation CSP or in general energy storage systems. If you operate with a molten salt, I think it's very important to consider intelligent gas management and understanding how beneficial some of these gas species can be in the long run. With that, I think we are at an end. If you have any questions, I'm very happy to answer them.
I think that out of curiosity here, testing of molten salt at a temperature more than the, let's say, nominal operating temperature in the CSP plant.
Yeah.
It is because you are looking at the tower application, so 600 and more, or for material, yeah, for the salt tower application.
So actually, the reason for us going to 620 degrees molten salt temperature was a different reason. There is, I think nobody has talked about it today, or at least Pedro has been starting this initiation. If we talk about process heat and using molten salts for other applications, one of the applications can be transforming coal-fired power plants into so-called storage power plants. You remove the coal part and you integrate storage. In principle, that's possible, and there's going to be a demonstration in Chile, to my best of knowledge. We wanted to get the molten salt systems to a broader range of coal-fired power plants. And modern coal-fired power plants operate at steam temperatures, let's say at or above 600 degrees. If you want to run these coal-fired power plants from molten salt systems, the molten salt needs to have a slightly higher temperature. And we defined this temperature to be 620 degrees for internal design as an internal design temperature. And this is why we started looking specifically at this temperature back in the day. And we are now extending this temperature. So we have experiments running in the lab where we are doing tests at 650 degrees to try to demonstrate that we can even upper the temperature more or less 100 degrees above the existing state-of-the-art temperatures. But the initial motivation was coal-fired power plants and their transformation. I don't know if Thomas is talking about it tomorrow, but you are? Good. So Thomas will tell you more about it tomorrow. Great. Thanks. Any other questions? Okay, if you have one, just feel free to contact me whenever, today, tomorrow, or Thursday. Thanks.
Thank you, Alexander, for your presentation. Very interesting. Also, this the fact that you are open to new application, new perspective for the use of molten salts. And the following lecture will be focused on corrosion topic again, and from a different approach and perspective. But this is an important, you know, this interest, the interest of the research on the topic of material compatibility is somewhat related to the you know, to the importance of materials compatibility when you look at the industrialization of this technology. Since the industry, when start to invest on this technology, obviously wants to know how many times the plant will work. So the lifetime of the system, of the components, and how much the degradation, let's say the reduction of the performance will be. And so this is a very important and hot topic, materials compatibility. And now, again, on this topic, I will leave the floor to Elisabetta Vega, who is a chemical engineer. She has earned her PhD at the Sapienza University. She has been working at ENEA since 2011, and her research activity is mainly focused on thermal and physical characterization of molten salt, study of material for thermal energy storage, experimental characterization of corrosion degradation on austenitic stainless steel for CSP application with molten salts.
So, good afternoon. I would like to show you some aspects taken from literature regarding corrosion of stainless steel in molten nitrate salts. First, a simplified example of a tank's thickness and the steel cost. The definition of velocity of corrosion, the reaction involved in corrosion process, and the relative oxide layer as product, and some best practice for material selection for material selection in molten salt corrosion and environments. Okay, this is an example. The energy to be stored is 1,300 megawatt hours using binary and ternary solar mixture. For binary, I mean solar salt, and for the ternary mixture, I mean the ITEC XL. In the table on the left side, I have reported the operating range temperature, the thermal properties of the mixture, and after that I estimate the kilograms of salt necessary to store the energy. And after that, I fixed the height of the tank equal to 12. And after that, I calculate the diameter and the dimension. After that, to evaluate the thickness of the tank, I made a big hypothesis, a very simplified hypothesis. I use Marriott-Barlow, the formula of Marriott-Barlow, that normally is not the right one, okay? Because to design a tank, you have to respect the requirements of the HASME or the HAPI code, okay? This is simply an example. And using Marriott-Barlow, I roughly estimate the thickness of the tank. You see the results for the binary and the ternary. To this value, normally you have to add or consider the over thickness for corrosion. But also this is normally included in the code that you are following. Okay, after that, calculate the thickness. The third step was to evaluate the volume of the steel associated to this amount of energy. And I roughly estimate also the cost using a reference of the Italian market stainless steel. I have plotted some literature data about corrosion. For example, looking to the black star, that it refers to the 316 stainless steel. Some discrepancies come out. Considering the 316 compared to the alloy 800. Some discrepancies come out, even though the data refer to similar experimental condition. In the paper was not presented an analysis of the error of measurements, and this discrepancy come out. Looking always to this graph, it is clear that in the range between 500 Celsius degree and 600 Celsius degree, you can choose a 10 micrometers per year or 15 micrometers per year, such corrosion rate. Okay. On the left side, there are all the definitions that you find in literature about the corrosion rate and all the variation of mass associated with the process. I also reported all the literature data that I used to plot the graph before, that I show you before. Okay, you can find all the reference here. I reported the data and also again the publication. Okay, the corrosion reaction for austenitic stainless steel are mainly constituted by the reduction of the nitrate in nitrite and the oxidation of iron in hematite and ferrite, in magnetite and hematite. Other steps are of formation are that the hematite reacts with chromium and given spinels of iron. And moreover, raising the temperature, there is nitrogen release, and this create another product that is the sodium ferrite. Okay, the oxide layer in austenitic stainless steel is mainly constituted by these compounds. This just an example of an XRD analysis which confirm that the mainly constitutions of the oxide layer is constituted by these corrosion products. Okay, from literature, the experience of SOLAR2 pointed out that the AZ300 exhibit a good corrosion properties. Just this. Now, thinking to a test, a practical test, one of the first best practice is useful to follow is to check the impurity in the salts, okay, that you intend to use, mainly for the chloride content, because chloride increases dramatically the corrosion rate of the stainless steel. From literature, it is reported that 0.2 is an acceptable percentage of impurity in the salt. As concerned the methodology for the corrosion test, the main steps are the test condition, the sample preparation, the gravimetric analysis, the descaling process, and the metallographic examination. The main procedure for the descaling process are the ISO standard. It is important to the main point of this procedure are to choose the right descaling method in order to totally remove the corrosion product and avoiding the attack of the bulk layer. This is it.
Are there any questions?
Thank you.
Okay.
Great.
Okay. So it seems that we are almost in time. So if you have from the on-site attendance or from the online attendance, if you have any questions related to molten salts and on different topics from the possible applications to to thermophysical properties to again corrosion or different aspects related to their use. I think that we have obviously here the lecturer to answer. And otherwise, you can for sure send us your question, and we will provide you obviously all the answers needed, and provide you also reference for in order to deepen the topic and to if needed to specialize and to focus on specific details. And I don't know if do you have any comments or questions, suggestions? Okay, I think that for today, I think that we can close the school. Tomorrow we will have another session that will be focused on the application of molten salts in different fields, so thermochemistry, so production solar fuels, and production for provision of solar heat to the industry, Carnot batteries, and also the presentation, the discussion on the practical aspects related to decommissioning, the operation, since as you have already understood, I think during this first session, the main problems related to the use, the main disadvantage related to the use of molten salts in plants, in CSP plants, is their low melting temperature, their low melting point, and so the need of avoiding freezing of these salts during circulation, the formation of cold areas where the freezing can start, and then obviously impact on the operation of the plants, requiring so very costly maintenance operation. And so this is one of the topics that will be obviously discussed tomorrow. And at this moment, I would like obviously to thank all the lecturers and the attendants for their interest and their attention. So good afternoon. And see you tomorrow at 9, okay?